everybody. My name is Wolf Geppert. I'm the chair of the European Astrobiology Institute. And it's my pleasure to announce a seminar today, which is actually the center of my interest and which actually made me join astrobiology. And I am happy to welcome Izaskun Jimenez-Serra from the Centro de Astrobiología in close to Madrid, I would like to say, in Spain. And the talk will be about, as I said, towards prebiotic chemistry in the interstellar medium. And I'm keen to hear more about it. Izaskun, the floor is yours. Many thanks for coming.
Thank you very much. It's really a pleasure to be here today. And thank you very much for the invitation, because it's really a great opportunity to show you the research that we are doing currently at the Astrobiology Center in Madrid, and in particular within the interstellar medium group in this center. And our intention is basically, or our aim is to try to connect the chemistry that we can find in the interstellar medium with the prebiotic content that could have triggered the processes leading to the origin of life. So, but before I move on, I would like to thank all my collaborators because this is a joint effort. So in this group of people, so we have astronomers, we also have biochemists such as Carlos Briones, mathematicians, physicists such as David Hofer, Jacobo Aguirre, and also spectroscopists. And I would like to point out that without their help, it wouldn't have been able, we wouldn't have been able to provide the discovery of so many prebiotic species as we've done in the past few years. And also with the help of material physicists, what we are trying to do at the moment is to try to understand how this prebiotic, or some of these prebiotic species may form in the ISM, in the interstellar medium. So this is what it looks like. So the Astrobiology Center, so it's about 30 kilometers off Madrid, so it's not exactly in Madrid, and it's in the interdisciplinary institute. And I have to say that it is very inspiring to be among different people and different groups doing or working on the different aspects of this big question, which is the origin of life. Then, as I said, so we are, so we belong to the astrophysics department, and in particular, we are astrochemists. So we are interested in the chemistry, so in all those reactions that molecules experience under the extreme conditions of the interstellar medium. And what we are interested in is to try to understand how they form, how they survive, and how complex can become that chemistry in space. Where do we find molecules? So this is a mix of the galaxy at different wavelengths. So we can go from the optical regime to the near infrared, mid infrared, so millimeter and far infrared. And the very first thing that one notices in this optical image are these dark patches. So these dark patches are molecular clouds. So they are not empty, but they are molecular clouds, and they are full of molecules and interstellar dust. Dust is very efficient at absorbing radiation of optical and ultraviolet wavelengths, and what it does is to re-emit that emission in the infrared, in the near infrared and far infrared. So all these bright regions in this image that we see in the far infrared and sub-millimeter are molecular clouds. So this is where we are going to find molecules, and where we will try to detect these prebiotic species in space. So this is a closer-in image of a molecular dark cloud, a molecular dark cloud core in particular. And as I said before, the conditions that we can find in this kind of objects are really extreme. As you can see, the temperatures are close to the absolute zero, so are of the order of 10 Kelvin. And also we are under high vacuum conditions, so the densities are very low, are of the order of 10 to the 3, 10 to the 4 particles per cubic centimeter. These regions, however, represent protective environments where molecules not only can form, but they can also survive, because also the external interstellar radiation field can be blocked by interstellar dust, and that's how molecules can be protected. So these are the kind of environments where we are going to find molecules and where molecules will form. Molecular dark clouds are also the regions of star formation and of planetary formation. So this is the very prototypical molecular cloud, the Taurus molecular cloud. And as you can see, there are certain regions that present higher densities, and because if they become a little bit more massive than the rest, they start collapsing gravitationally, forming these condensations. And then within those condensations is where a new protoplanetary system is going to form. And then it would look, when it is young, so it would look as HL Tau. This is one of the iconic images delivered by ALMA, by the Atacama Large Millimeter Array. And as you can see images, we have started probing a similar spatial scales as the ones typical of our solar system. So by performing these observations, so we can probe all the chemical content throughout the whole process of planetary formation. And this is our main goal. Our main goal is to try to understand how we can go from the very simple chemistry that we find at the initial conditions of solar system formation, solar type formation, represented by prestellar cores, how that chemical complexity evolves or increases once a protostar appears in the system, and then how that chemistry evolves into protoplanetary disks, how that organic content is incorporated into planetesimals, and then finally what we think is that this organic content, this organic material could have contributed to the first biochemical processes that led to the origin of life. Of course, this is a very long process with many intermediate steps that we think that the connection between all these different processes could be provided by what we call, what we name complex organic molecules. So for those who are not familiar with what we mean by a complex organic molecule, this is for astrochemists. So this is the definition that works for astrochemists. So we define complex organic molecules as carbon-based compounds with at least 6 atoms. So for example, methanol is one of the simplest complex organic molecules that we can find in the interstellar medium in space. A subset of these complex organic molecules can be called prebiotic, because we believe that they may have been involved in the first steps in the origin of life. Some examples of those are represented, for example, by glycolaldehyde, which is the simplest sugar-like species, glyceraldehyde, which is the next in complexity. So glycolaldehyde has 2 carbon atoms, and this glyceraldehyde has 3 carbon atoms. Then we also have urea, a very important prebiotic molecules, as I'll mention later, and glycoladehyde, which also appears in some of the chemical schemes of theories of the origin of life, such as the primordial RNA-world. But how do complex organic molecules form in the interstellar medium space? So it was early recognized, so in the late 90s and in the 2000s, it was found that methanol, which is as I said before, one of the simplest complex organics, could not form in the gas phase, just by gas phase reactions. So interstellar dust grains had to act as catalysts for the formation of these complex organics. So that's why, for a long period of time, so over basically 15 years, it was believed that these complex organics formed mainly on the surface of dust grains. So the two main mechanisms proposed for the formation of these complex organics were the ones that are listed here on the slide. The first one, hydrogenation, which what we have is a hydrogen atom that lands on a surface of a dust grain, and then because hydrogen atoms are very light, so they are highly mobile on the surface, and they can move on the surface even at very low temperatures. So when they encounter heavier atoms or radicals, they react and then they create larger and larger molecules. So this is the case of methanol that is formed in this way from carbon monoxide, for example. Then the other mechanism that was proposed early on was these radical surface reactions. In this scenario, however, it is required that the temperature of the dust grain has to be higher than 30 Kelvin. The reason for this is that we have these radicals on the surface. They are heavy or heavier than hydrogen atoms, so they need a higher temperature to become mobile on the surface, so that when they move or they diffuse on the surface, they can encounter, they react, and then they form larger complex organic molecules. So these were the two main mechanisms proposed until very recently, actually. However, so thanks to new instrumentation, especially high sensitivity instrumentation at the telescopes, it was found that these complex organics appeared even under the coldest conditions in the interstellar medium, such as the molecular dark cloud core that I showed at the beginning, with temperatures of the order of 10 Kelvin. Then under these very extreme conditions, under these very cold conditions, it is very difficult to explain the formation of these complex organics just by invoking the hydrogenation or the radical diffusion mechanism. So due to these new observations, there was a huge effort, or there is a huge effort still within the community, within the astrochemistry community, to try to understand how these complex organics form. And this is one of the possibilities, is that some, or at least some of these complex organics can form also in the gas phase. And this is the example provided by Dimitris Skouteris, in which by injecting a small amount of ethanol, he could produce, or he could obtain all these family of complex organics from formic acid to acetic acid, acetaldehyde, formaldehyde, or glycolaldehyde, just by using gas phase reactions. But just to give you an idea of how active this field has been in this topic, there has been many other mechanisms proposed in the past few years. I listed some of them in here, and I would just like to point out the example, for example, of Fedosef in 2017, where they could produce all these different sugars, increasing in complexity, by invoking, or by this new mechanism that has been proposed, non-diffusive formation on dust grains, which involves that radicals, they don't need to move on the surface. So the radicals, once they are formed in the same, in situ, in the same location on the dust grain, they can react, and then they form these larger complex organics. So this is just to give you an idea of how active the field has been, and that this is really a hot topic now in astrochemistry. But where do we find complex organic molecules? So as I said before, so complex organic molecules, and thanks to the new instrumentation, are found in many different environments of the interstellar medium. In fact, they seem to be ubiquitous in the interstellar medium. So we find them in the star-forming regions, in the dusty cocoons around massive protostars and low-mass protostars. We also find them in molecular outflow, so in this material that has experienced violent supersonic motions or shocks. Also in the harsh environments or photon-dominated regions, so even in the presence of strong UV radiation fields. Also in molecular dark cloud cores, stellar cores and starless cores, on these very cold condensations at these very cold temperatures, as I mentioned before. And also they are ubiquitous across the galactic center and in the giant molecular clouds of the galactic center, as I'll show you later on. So these complex organics are found across the full central molecular zone of our Milky Way. Now, the first regions where different groups started looking for complex organic molecules and also in particular prebiotic molecules were star forming regions, and in particular these two different types of objects, the hot cores and the hot corines, which are these dusty cocoons, dusty envelopes around massive protostars and low mass protostars. And the reason for this is that these objects are very hot, so they present relatively high temperatures, higher than 100 Kelvin, so from 100 to 300 Kelvin. And because of this, the ices, the ice mantles of interstellar dust particles, they are thermally dissolved, so they are evaporated and then they are incorporated into the gas phase. So they are basically prime targets for searching new or complex organic species and for the discovery of new prebiotic molecules. And in this regard, so I would like to mention the work done by Jorgensen with the PIL survey and Arnaud Beloche with the MOCA and RIMOCA surveys, who have targeted these two different types of objects, a hot corino, IRAS 16293, and also the Sagittarius B2N high mass star forming region. And as you can see, they have been able to provide a detection of new complex organic molecules of prebiotic interest, such as glycolaldehyde for the first time in a low mass region, formamide, methylacecyanates, acetic acids, but also other prebiotic species such as amino acetonitrile, which is a precursor of, believed to be a precursor of glycine, also isopropyl cyanide that I will mention just in a minute, urea and other prebiotic species, and then methylformamide. So all these works have really provided a view of the high level of chemical complexity that this kind of object presents. One particular case that I really like very much is the detection of isopropyl cyanide, which was actually represented the first detection of this branched molecule. And this was the work reported this was the discovery reported by Arnaud Beloche in 2014. So this discovery actually represented a breakthrough in astrochemistry, because amino acids also present this branched structure. So this opens the possibility for this kind of molecules to form in the interstellar medium. Another one that is also those that are also very relevant for prebiotic chemistry are urea, which is a prebiotic molecule precursor, as I'll show you later on. And also I would like to mention the detection of propylene oxide, which represented the detection of the first chiral molecule in the ISM. And this was reported by Brett McGuire in 2016. So as you can see, these regions have been really prolific in the discovery of new complex organic molecules and prebiotic species. Now, the problem with these regions is that their spectra, their observed spectra, is really populated by hundreds or by thousands of molecular lines. So they are highly, they suffer from a high level of line blending and line confusion. Then in the past few years, we have seen within this field that there is a trend to move to another different, or to a different type of sources that suffer less from this problem, that suffer less from line blending and line confusion, such as molecular dark cloud cores and starless cores, stellar cores. And in this regard, I would like to mention the work of Pepe Cernicharo's group using the Jeves 40-meter telescope, and a group of Brett McGuire using the Greenbank telescope, where they have been reporting. They have been reporting all this discovery for these aromatic molecules that are believed to be precursors of polycyclic aromatic hydrocarbons in the Taurus molecular cloud. So in this particular core in TMC1. So as you can see, so these are ring-like molecules. So the level of chemical complexity that we can find in these molecular dark cloud cores is really impressive. So now the next task is actually to try to understand how these molecules can form under these extreme conditions. So this is something that I guess we will be seeing in the next few years. Now, what has been our approach? So our approach is slightly similar. So we have been targeting another type of objects, which are the center giant molecular clouds. Then these giant molecular clouds are not cold as the ones Taurus molecular cloud. So they are located, I think there's a little bit of noise, background noise. So I don't know whether there's any question. So there's our approach, as I was saying, is this giant molecular clouds, is to look for this, to look at these giant molecular clouds located in the galactic center. These giant molecular clouds show a very high level of chemical complexity, and the ones that have been inspected by the group of Martín Pintado and Requena Torres in the early 2000s, they showed a very similar level of chemical complexity throughout the full central molecular zone of the Milky Way. In particular, we have been focusing on this GMC, and this giant molecular cloud, G+0.693, which is a quiescent giant molecular cloud, quiescent in the sense that it doesn't show any sign of star formation activity. So the physical properties of this cloud are listed here. So it shows densities of the order of a few 10⁴ particles per cubic centimeter. And as you can see, the temperature of the dust and the gas are decoupled, so they are completely different. The dust temperature is lower than 20 Kelvin, while the gas temperature is higher than 100 Kelvin. The special thing about this cloud is that it shows an excitation temperature which is very low due to the low H2 gas densities. So the molecular excitation, or the molecules that we detect towards these type of clouds, show excitation temperatures lower than 15 Kelvin, which really helps, which is really an advantage for the discovery of new complex organic molecules, and in particular of organics of prebiotic interest. So these low levels of these lower excitation temperatures helps in reducing the level of line confusion, of line blending, because only the lowest levels of the molecules can be populated at these very low temperatures, and then this makes the spectrum that we see relatively cleaner with respect to what we would see in massive hot cores or in low mass hot corinos. So this is the reason why we are using this particular giant molecular cloud located in the galactic center. Even though, as I said, the line blending, the levels of line blending and line confusion are much lower, here, as you can see in this example of the surveys that we have carried out at different wavelengths, at 7 mm with the Jeves 40-meter telescope, and at 2 and 3 mm with the ISM 30-meter telescope, you can see that the observed spectra are full of molecular lines. So it's really a challenge to do the analysis of these surveys. So what we have found so far is that there are over 120 species detected, and more than 50% of them are complex organic. So this is probably one of the sources in our galaxy with the highest reservoir, with the largest reservoir of complex organics in the Milky Way. So when I said that it is rich, chemically rich, so it's not only rich in oxygen-bearing molecules, but also in nitrogen-bearing molecules and also in sulfur-bearing molecules. So we have been able to provide detections for all these different types of molecules from all these different types of families. So this is also an advantage, because then we can cover a wide range of families in only one single object. So now we have the source. So what is our approach? So how did we approach the detection of prebiotic molecules? So by talking to people at CAB, such as Carlos Briones, who is an expert in theories of the primordial RNA world. So we started inspecting the chemical schemes proposed for this RNA world scenario, and in particular, so we started having a look at this work of the group of Sutherland, who is now in Cambridge, and in particular these two publications, the ones from Pauner in 2009 and Patel in 2015. So this diagram actually belongs to the paper published by Patel in 2015. And as you can see, in this chemical scheme, they start from very simple molecules that are actually very abundant in the ISM, from HCN and formaldehyde, and then they start building up a whole chemical network, chemical scheme that not only generates the pyrimidine ribonucleotides, which are the building blocks of one of the types of building blocks of RNA, but also provides precursors, or is able to generate amino acids, sugars, and lipid precursors. So we started having a look at this scheme. So if we zoom in, and the very first molecule that one finds is this glycolaldehyde, and actually this is a key intermediate species in the production of sugars with 3 and 4 carbon atoms. This, by having a look, by inspecting the data available in the ALMA archive for this low mass protostar area 1623, then we realized that glycolaldehyde was detected, and this represented the first detection of this molecule in the ISM in the interstellar medium. Now there's also some recent work by Lichtering that was published last year in 2021, where they also report the detection of glycolaldehyde in another star-forming region. I think it's in Serpent. So as you can see, this type of molecules seem to be more common than what we originally thought. So encouraged by this discovery, so then we decided to move on in the chemical scheme and then inspect the other molecules to see whether we could detect the other molecules in this chemical scheme. So in this particular case, so we started by targeting urea, 2-aminoxazole, glyceraldehyde, and the hydroxyacetone. And then we looked at these molecules in our giant molecular cloud in the Galactic Center. These sugar precursors, glyceraldehyde and the hydroxyacetone, were not detected. So we, however, obtained upper limits that we believe can be improved quite a lot. So because the first data that we had was much less sensitive than what we have now at the moment. But this non-detection was consistent with previous searches by other people in the past, such as Aponi in 2006. Interestingly, we were able to detect urea, so we were not the first ones, because the first one in reporting urea in the ISM was Arnaud Beloche, as I mentioned before. So with this detection, so we also demonstrated that urea could also be found in other regions in the ISM. So we think that urea is actually more common than what we think. So the abundances, as you can see, so we are reaching abundances which are quite low. So this gives you an idea of how challenging is to detect this kind of prebiotic species. We also searched for 2-amino-oxazole, and this was the first time that this molecule was searched for in the ISM. The upper limits, again, I think can be greatly improved. And as you can see, so these key intermediate species in the formation of pyrimidine ribonucleotides was not detected. These raised the interest in the material physicists such as Belén Maté and Víctor Herrero, and then they decided to try to understand the chemistry of a 2-amino-oxazole on the surface of gas grains, and in particular how this molecule reacts with the processing of interstellar ices with UV radiation, and also simulating the impact of cosmic rays by using high energy electrons. So by doing these experiments, they used both a pure and mixed ices 2-amino-oxazole, and then they could establish the photodistraction rates. And the interesting result is that they could provide an estimate of the lifetime of a 2-amino-oxazole under different conditions. So for example, in these molecular clouds, the lifetime for 2-amino-oxazole is relatively long, so it could last, it could survive longer than 10 to the 8 years. However, if these 2-amino-oxazole, this molecule, were present in objects of the protosolar nebula, it would be readily destroyed. So it would be destroyed in very short time scales of the order of 1,000 years. So this could pose some problems for this chemical scheme, because this would mean that 2-amino-oxazole is destroyed very easily, and it couldn't proceed farther down in the chemical scheme proposed by Patel. Now, the alternative scenario was proposed by the group of Thomas Carroll in this paper published in Science by Becker and collaborators, where they proposed a new way of generating purines and pyrimidine ribonucleotides by starting from species, like simple species that we find in the ISM, formaldehyde, glycolaldehyde, but also they pointed out the need of these two species, urea, which we already had in our cloud, and also hydroxylamine. So the next step that we decided to take was to inspect hydroxylamine, whether it could be found in our cloud. And this was the result. So this is the work of Victor Rivilla, who also works with us at the Astrobiology Center. And here, as you can see, we could detect not only these 3 rotational transitions, the 2-to-1, 3-to-2, and 4-to-3, but also the hyperfine components. So we had a very clear detection of hydroxylamine, which was the first one of these species reported in space. Because this cloud is also very abundant in amines, then Victor also started looking for other amine-like species, and then he realized that this other molecule, ethanolamine, was also present and very clearly detected in our giant molecular cloud. Ethanolamine turned out to be a very interesting molecule because it is the simplest phospholipid head group. So we have here there are 2 types of phospholipids. This is one of them, and as you can see, the phospholipids form part of cell membranes, of the actual cell membranes, and this is where ethanolamine. So this is the head group. We have also phosphates. I think we have I think it's a glycol and the fatty acids here. So as you can see, so ethanolamine is the head group. We also estimated the abundance, and this abundance allowed us to estimate the ratio between ethanolamine and water. And actually that ratio, abundance ratio with respect to water, was consistent with what we find in meteorites. So these, what we proposed in this paper published in PNAS is that ethanolamine could have been available in the LEF, and could have been available for the formation of cell membranes very early on. Now, besides this detection, so we have also detected other species that are related with different prebiotic scenarios or prebiotic chemistries. So we have detected this cyanamidyl radical, is a precursor of other prebiotic species. Also ethyl-isocyanate, so we have expanded the family of peptide-like molecules. We have been able to provide the first detection of a thiol, of thioformic acid, which thiols, as you may know, they are good catalysts in the synthesis of prebiotic proteins, and also of these amines, vinylamine and ethylamine, which are believed to be precursors of amino acids. So these are all the molecules that we have detected, reported so far since 2019, and we are still working on a few more detections. So stay tuned because we will have several more that will come out in the next few months. Now, of course, the detection of these new species have triggered also some related works, side works, on the chemistry of these species, and I invite you to go and have a look at these papers. They focus in the isomerization of some of these species, especially the imines, and also of the thio and formic acids via detailed quantum tunneling calculations, and also they focus on the formation of thioformic acid on dust grains, which is the work led by Germán Volpe-Pérez. So if you're interested, please go and have a look at those papers. Now, in the last 5 minutes, so I would like to mention what is next. So what are our next steps? So we have improved our spectral survey, especially the one that we carried out at the Jimenez telescope. The one that we initially used was just 30 hours of observing time, and now we have over 130 hours of observing time. So we are in the process of analyzing, reducing those data, and then we will start with the analysis of the new survey soon. So we hope that we can provide many more detections, because now we are reaching noise levels below the millikelvin RMS noise. And then the other possibility, that is something I would like to conclude with, is to perform spectroscopic surveys at low frequencies, but against a bright background continuum source. And this is something that has just come out. This is something that I was asked to prepare for a special issue of Frontiers, of the Frontiers magazine or a journal, and so they asked me to write the impact of interferometers such as the SKA, which operate at lower frequencies. And I think that these kind of instruments, especially the ones operating at these low frequencies and in the Q band, they can provide very important input or new discoveries, especially for even larger complex organic molecules and prebiotic molecules, such as, for example, these sugars with 3 and 4 carbon atoms. The trick here is to perform the experiment, the detection experiment in absorption against a background source, because there we can gain quite a lot in signal to noise ratio. So if you're interested, so this is something that I posted recently on the archive, and I think it has been published today. So it's open access, so you can go and have a look. And just to conclude, so this is my summary. The precursors of prebiotic chemistry form in the ISM. Then what I personally think is that these low excitation temperature sources present a huge number of advantages for the search and for the discovery of new prebiotic species in space. And I think that the way to move forward is to carry out these searches at low frequencies. So either in emission or in absorption, but in absorption is definitely something that we should explore in the near future, and we have started thinking about it. And just to finalize, just to say that within the National Research Council, so there has been now created a network of the different groups who are trying to address the different aspects in the whole process, or in the long process, from astrochemistry to biochemistry, prebiotic chemistry, and then to finally the origin of life. We had our first meeting last week. It was very successful, so we are trying to create all these connections to try to provide some hints or some answers to these to the different aspects of this difficult question. And with this, I just finished my talk, and I'll be happy to take any questions.
Yeah, there is Eva, please. Go ahead.
Okay, thanks a lot. It's a wonderful talk. Thank you so much. And I have a general question just about the differences in the different part of the galaxy. I mean, you discuss in the full extent the complex organic molecules you found in a giant molecular cloud close to the center of our galaxy. But could you comment what are, if there are, any differences in the content of these organic molecules? I mean, depending on where they are in the molecular clouds are in the galaxy.
Yeah. Thank you very much for the question. So that is really a great question. So we are targeting this cloud in the Galactic Center because, as I said before, it's one of the main reservoirs of complex organics. So if we really want to have a chance of detection, we really need to go for these type of targets because they are really rich and they have a lot of material in the line of sight. So we increase the chances of detection. Now, as you pointed out, then the chemical composition may change depending on the physical conditions of the source. And actually, as I said before, so these complex organics are found in many different types of environments, but that composition may change depending on whether the UV radiation field is more extreme or is higher or not, if it photo destroys the molecules or not. Actually, in the the Galactic Center, so that was, it was found that in those giant molecular clouds that are more exposed to UV radiation field have a lower amount of complex organics. So there's definitely an effect of the different physical conditions. Now, you may wonder also how is this relevant to the chemical composition in, for example, protoplanetary systems, no? Then our approach is to try to understand how complex can the chemistry become in the ISM. And then this is why we are targeting all these different types of objects. But even, you know, in the very cold conditions, so in this Taurus molecular cloud, we find this huge level of chemical complexity. And actually, the process of the formation of a protoplanetary system is not quiescent. So in the sense that it goes through several violent processes that can actually simulate the physical conditions that we find in the Galactic Center. So some of the protostars are known to be sources of cosmic rays, which are actually quite high in the Galactic Center. There are also these events, burst events in these class 2 objects, FU or ionins, I think. So there are these bursts, violent bursts, and that also affects the chemistry. And actually that may help in understanding the complex organic content in these disks. No, as that's the work of Lee, I think, in 2020, I believe, or 2019. So I believe that there are similarities, there may be similarities with what we find in the Galactic Center and the different stages in the process of solar system formation, because it is a very complex process, and you also find these different physical conditions throughout that process.
Great, thanks a lot. So there's no any gradient which you can see, I mean, on a robust feature where here you cannot find this complex organic molecules, but in the Galactic Center you can. So this is rather more connected with the sort of more local environment.
In principle, yes. So that's our goal. Our goal is to try to connect what we find in the Galactic Center also with other sources that may be close to star-forming regions and then to the process of planetary formation, let's say. And that's something actually that Victor Rivilla in our group is working on. So they are trying to compare the abundances of some of these species that are detected in these different types of environment, and then see whether there is a connection or whether there is actually a trend from that point of view. We can only do it with a few molecules, because you see, so it's very difficult to detect, the molecules such as urea, but with the ones that are available, that's what he's doing.
Sure, thanks a lot. Thanks a lot.